Okay, so let's continue with our Diophantine equation solutions. So here we have 4 Diophantine equations, and we have to not only solve them, but we have to in fact find all positive integer solutions, that is those solutions in which both x and y are positive integers. If such solutions exist, we have to find them. So let's see the solution, our solution. So we know the procedure. First of all, we have to calculate the GCD of 18 and 5, which we do by using the standard Euclidean algorithm, where we repeatedly do division. So here are the equations. Okay, so here we have divided 18 by 5, so the remainder is 3. So next we will divide 5 by 3. The remainder is 2. Next we divide 3 by 2. The remainder is 1, and actually you can already see that 1 will be the greatest common divisor, but still let's write the last one just for the sake of writing. So you get the 0 remainder and the process stops here. The last non-zero remainder is 1, so that is the GCD. Hence, since 1 divides the right hand side, 48, the given Diophantine equation has a solution. Now, in order to calculate this GCD, actually we do not have to go through this process, because here in this particular case the numbers are rather small, only 18 and 5, which we can just simply see that the GCD will be 1. That is because 5 is a prime number which does not divide 18. So, what are the common divisors, what are the positive divisors of 5? Since 5 is prime, only 2 positive divisors it has, 1 and 5. Among them, 5 does not divide 18. So the only common positive divisor is 1. So that is the GCD, greatest common divisor. But we still go through this process because we will need to express 1 as a linear combination of 18 and 5 in order to find a solution to this. One particular solution from which we will find all the general solutions. So that's why we go through this process. Now we do the things in the other direction. Using this one, we get 1 equal to 3 minus 2. Then we replace 2 with 5 minus 3, that is 3 minus 5 minus 3. So that gives us 2 times 3 minus 5. Then we replace 3 with 18 minus 3 times 5. So 2 times 18 minus 3 times 5 minus 5. Okay, so what do we get here? This will be 2 times 18. So writing it like this, we get 18 times 2, and here these two things will give us minus 6 times 5 and one extra minus 5, that means minus 7 times 5. So 5 times minus 7. So this combination is equal to 1, but we do not want 1 on the right side, we want 48. So we multiply on both sides by 48. So 48 is equal to 18 times, what will it be? 96 plus 5 times minus 7. Okay, I dare to do it like this. Let me see if I have found the correct answer. 96 and minus 3, yeah, at least this much I can do. Okay, so a particular solution is x naught equal to 96 and y naught equal to minus 336. And now we will write the general solution. So the general solution, let's erase these things. General solution is x equal to, let me just for the sake of recalling write the formula. X naught plus b divided by d times t, where x naught is this, and if our original Diophantine equation is this, then this is b, that means b is the coefficient of y. What was our equation? 18x plus 5y equal to 48. Yes, so that means for us b is 5, but for us d is the GCD, which is 1. So here we do not have to divide by anything actually. So it is x naught is 96 plus 5t. Okay, so this is the general x value. Similarly, y is equal to y naught minus a divided by d times t. Y naught is minus 336, a is 18, d is 1, t, where t is any integer. T freely varies over the set of integers. For any integer t, this pair will give us a solution, and conversely they are all the solutions. Okay, so they form a general family of solutions where all the solutions are available. Now from these solutions we have to see which ones are positive in the sense that where both x and y are positive. So that's the next thing we do. For a positive solution, because we have found the general solution, we have the expressions for x and y. So we can now investigate when these expressions become positive, for which values of t. For a positive solution, we require this to be positive, that is, let me write like this, 96 plus 5t must be positive, and simultaneously this should also be positive. Minus 336 minus 18t should also be positive. Now this implies what? T is greater than minus 96 over 5. And what about this one? Minus 18, you can, if you want, you can multiply on both sides by minus 1 2, or you can directly do like this. Okay, now let us see this, what these values are actually. I mean, if we express them in decimals, t should be greater than minus 96 divided by 5, which is minus 19.2, and t should be less than, let me write t first, then it should be less than minus 336 by divided by 18, which is approximately equal to this. Actually the 6's go on and on like that. Okay, so this means what? This means that t has to be less than minus 18.6666, and at the same time t has to be greater than minus 19.2. So there is only one value of t that will satisfy both of these inequalities, and I mean only one integer t, and that integer is t equal to minus 19, because minus 19 is greater than minus 19.2 but is less than this value. So this implies t is equal to minus 19. This is a consequence of the fact that t must be an integer, that's why. So the only positive solution, there are infinitely many solutions. For each integer t, we will get a pair that is a solution to our Diophantine equation. But among them, there is only one positive solution, and that comes for the value t equal to minus 19. So if you use this, 96 plus 5 times minus 19, this becomes 1 and y equal to minus 336, what was it? Minus 18t, minus 18 times minus 19, and this turns out to be equal to 6. So x is 1 and y is 6, that is the only positive solution. Now part B. In part B, let me just simply write the equation first so that we can see what we are doing. In the actual solution, this need not be written, of course. So here we are first of all dividing 54. So again we have to calculate the GCD of 54 and 21. So the relevant equations are these: plus 12, then you divide 21 by 12, then you get 1 times 12 plus 9. Then you divide 12 by 9, the remainder is 3, and divide 9 by 3, the remainder is 0. So here the process stops. So the greatest common divisor of 54 and 21 is equal to 3. Since 3 divides 906, the given Diophantine equation has a solution. Now we go through that back calculation process. So our GCD now is 3. So first of all, 3 is 12 minus 9. Then we replace 9 with 21 minus 12. So 12 minus 21 minus 12. That means we will get 2 12s and 1 minus 21. Next we replace 12 with 54 minus 2 times 21. Minus 21. So this is 2 times 54 and minus 4 minus 1, that means minus 5 times 21. Okay, so 3 is equal to this, but we do not need 3, we need this. So that means we have to divide on both sides by 302. So doing that, we get this. I mean we do not have to divide, we have to multiply on both sides by 302. So doing that, what do we get? We get this. Let me write the final thing. 54 times 604. That means 504 times 302. That this is what you get. Plus 21 times minus 5 times 302, which is 1510. minus 1510. And on the right side, of course, we have 906. Okay, so this gives us a particular solution to our Diophantine equation. So a particular solution is x equal to 604 and y equal to minus 1510. Hence, the general solution is x equal to x not, let's just keep on writing that thing so that we don't make any mistake, plus b divided by d times t. So what is our x naught? 604. And what is b? b is 21, right? Because this is b, this is a. 21 divided by our GCD. Our GCD is 3, that means 7. So plus 7 t. And y is y naught minus a divided by d times t. Y naught is minus 1510 minus a is this divided by 3. So that means 18 times t, where t is any integer. So that is the general solution. 604 plus 70 and minus 1510 minus 18t. Yeah, okay. So let's now seek the positive ones. For positive solutions, we require this to be positive and this one also to be positive. Okay, so this one gives us, the first one gives us what? T greater than minus 604 divided by 7, and while calculating with this type of inequalities, always keep in mind that when you are dealing with addition and subtraction, you do not have to bother about anything. But when you are multiplying or dividing by something, if that something is positive, then the inequality stays like that, it keeps its direction. But if it is negative, then the inequality is reversed. That thing you have to keep in mind. So what I am saying here is that if it feels somewhat inconvenient to skip steps, do not skip steps. Go through all the steps. For example, here we are going to multiply on both sides by 1 over 18, which is a positive real number. So that's why it will be like this only and not this. Okay, so now if you take things in decimal, then we get these values. So t is greater than, all of these are approximate values, minus 86.2857, something like that, it goes on, but we do not need that. We just need to see where the number lies roughly with respect to the integers, and at the same time t is less than, this one is minus 83.8, it goes like this, 8888 and so on. So here actually there are some, unlike the previous case where we had only one value of t equal to minus 19, here we have some choices. So t must be less than minus 83 point something. So t can take the value minus 84, it can also take the value minus 85, it can also take the value minus 86, but not minus 87 or lower integers, because t has to be greater than this. So here there are three choices for t. And corresponding to each such choice, we are going to get one pair of x and y values that will give us one solution. So three positive solutions will be found. Corresponding to these values of t, we have the following positive solutions. And those solutions, you can calculate these solutions, and their values turn out to be, oh, I wrote minus 84 first, so that means I'm keeping that order. So for t equal to minus 84, these are the values. X is 16 and y is 2. Then for t equal to minus 85, the values are x equal to 9 and y equal to 20. And for t equal to minus 86, the values are x equal to 2 and y is 38. To calculate these values, you of course put that these t values in the general solution, then from there you get x and y. So you can see that in each case both x and y are positive. So among all the infinitely many solutions, these are the only positive solutions where both x and y components are positive. Okay, so that is part B. Then we see part C. In part C, the equation, the numbers are increasing now. 123x plus 360 y is equal to 99. So first we divide 360 by 123. Doing that, we get 2 times 123 plus 114. Because I have gone through this calculation once and found that they are correct, so I am just simply copying it from what I have written here, but still you please go through them yourself to see if they are actually there is no mistake. Make sure of that. And then we divide 123 by 114, because mistakes are very common when we are in any, not just with numerical values, anywhere mistakes are inevitable. The best we can do is we can check again and again and make sure that there is no mistake as far as possible. Okay, so then we divide 114 by 9. So that gives us what? 12 times 9 plus 6. And then we divide. Now the numbers are very small. 9 by 6. So 1 times 6 plus 3. And in the very next division, the process stops because 6 is divisible by 3. Hence, our GCD here, like the previous one, is also 3. Hence, $123 and 360 is 3. Since 3 divides the right hand side, 99, the given Diophantine equation has solutions, has a solution. Anyway, you can write. Now to find a particular solution, we go through that process again. First, 3 is 9 minus 6. Then 6 is 114 minus 12 times 9. So this is minus 114 plus 12 times 9 plus 9 means plus 13 times 9. Then 9. So 9 is 123 minus 114. So minus 114 plus 13 times 123 minus 114. So this is 13 times 123 minus 13 times 114. Minus 114 is minus 14 times 114. And there is one more, no? This one. So here we replace 114 with 360 minus 2 times 123. So 13 times 123 stays like this, minus 14 times 360 minus 2 times 123. So the original equation starts with 123. So we are going to first of all write the 123. So this is what minus 14 times, do not forget that there is a minus sign here. So minus 14 times 2 is 28. That means I'm so bad with this sort of mental calculations. 13 plus 28, 41. Okay, I cannot do it unless I write it down. 123. And plus 14 times 360. But that of course is not what we want. We want 99, but we have 3, so we have to multiply on both sides by 33, and doing so this implies what? 123 times what is our x value? 41. 41 times 33 is there a mistake? I think, yeah. See, just now I was saying do not forget there is a minus sign. I myself have forgotten that this will be minus. Man, that's how mistakes are made. Anyway, so this implies 123 times, where do I have it here? Oh, okay. 135, okay, that's quite big. 1353, that is 41 times 33 plus 360 times, this one will be minus 462, which is 14 minus 14 times 33, that is equal to 99. So a particular solution is x not equal to 1353, 1353, and y not equal to minus 462. So now we write the general solution. Hence, the general solution is x equal to x naught minus b divided by d times t. I have gotten rid of the actual equation, but you can see the equation here itself. 123x plus 360y equal to 99. So our x naught is 1353. This is plus b divided by d, which is 360 divided by what was our d? 3. So that means 120 t, and y is equal to y naught minus a divided by, this one is minus. But there is one point that I must let's just see one thing here. I said that this is plus and this is minus. That's how the formulas are given in the text. But actually that does not matter. You know why? Because you have this arbitrary constant t here. No? So in place, because t is anyway varying freely over the set of integers where we have both plus and minus. If you accidentally write minus here but then write plus here, essentially nothing changes, because that means you are replacing t with minus t, which ultimately gives you the same set of solutions. Okay, so that is not a mistake, but do not write both in both the formulas plus or in both the formulas minus. That will be a mistake. Okay, so now, so what is our y naught value? Minus 462, and 123 divided by 3, that is 41 minus 41t, where t is an integer. Now we seek the positive solutions. For positive solutions, we require both of them to be positive. So 1353 plus 120t should be positive, and minus 462 minus 41t should also be positive. That means t should be greater than this, and minus, let me do it directly, write like this, okay, because you can take 41t on that side. Informally speaking, take 41t on that side. Actually we just say things like this in order to remember. Of course 41t is not physically moving there. No, we add 41t on both sides, which is allowed by the rules of inequality, and then this one vanishes and that one is left on that side. But informally, when we say such things like 41t minus 41t goes on that side and becomes plus 41t, it's just it is just to remember what ultimately happens, the ultimate result. There is no physical movement involved. So here the decimal values are, this is approximately minus 11 point, although it does not matter what comes after the decimal point, but still what is it, 275. And here t is less than approximately minus 11.26829. You can write 2683 if you want. Okay. Now t should be less than minus 11.26829. and t should be greater than minus 11.275. If you imagine on the numbered line, say this is your minus 11, this is your minus 12, so minus 11.26829 is here somewhere. and minus 11.275 is slightly closer to minus 12 because it is a little more minus, and t should lie here. So can t be an integer if it has to satisfy these inequalities? No, there is no such integer t. So that means there is no positive solution. So how we started this calculation, we wrote that for positive solutions we require these things, but it's not possible. But this is not possible since t is an integer. So the consequence is this. So there is no positive solution. That means among the infinitely many solutions, all of them are such that at least x or y is negative. Both can be negative also, but you won't get any solution where both x and y are positive. Okay, so that is part C, and now finally part D. Here the equation is this: 158x minus 57y is equal to 7. So let's see what the GCD turns out to be. Actually, see, there is one thing that I should explain a little, perhaps, is that if we compare this Diophantine equation with our standard form, what is B? B is actually minus 57. But now we will go through the Euclidean algorithm process to calculate the GCD of 158 and 57. But that will also be the GCD of 158 and minus 57, because when we calculate greatest common divisors, the signs do not matter. The signs of the numbers involved, they do not matter. This we already discussed before. So getting rid of the minus sign while calculating the GCD will get us, will simplify things. We do not mention anything about this though. We have, so 158 is equal to, here is the calculation, 2 times 57 plus 44. So here the 44 is our remainder. Next we divide 57 by 44. 1 times 44 plus 13. Next we divide 44 by 13. Plus 5, and then 13 by 5. You can understand that ultimately we are going to get 1. So the GCD is 1. GCD of what? 158 and 57 is 1, and now here we write, and as a result 158, sorry, I said 157, 158 and minus 57 is also equal to 1. It's essential to mention this because according to the theory that we have for the solvability of this type of equations, we want the GCD of A and B to divide the right hand side, and here B is minus 57. So unless you are mentioning this, you cannot then claim that okay, there is a solution. Now we can claim, since 1 divides 7, the given Diophantine equation has a solution. Now let's find a particular solution. So we go through the arduous process of the going back. So 1 is first of all 3 minus 2, then 2 is 5 minus 3. So that means we get 2 times 3 minus 5, then 5, no? 5 or 3? 3. 3 is 13 minus 2 times 5. Now I think okay. What the hell have I written here? I am replacing 3 with 13 minus 2.5. 2 times 5, sorry, minus 5. Okay, so this gives me 2 times 13 minus 4 minus 1 is minus 5. Yeah, now I replace 5 with 44 minus 3 times 13. So this is 2 times 13 minus 5 times 44 minus 3 times 13. So that gives me what? Minus 5 times 44, and minus 5 times minus 3 is 15, plus 2, 17. Okay, now next I replace 13 with 57 minus 44. Minus 5 times 44 plus 17 times 57 minus 44. Okay, so that gives me what? Minus 17 and minus 5. That means minus 22 times 44 plus 17 times 57, and finally I replace 44 with 158 minus 2 times 57. Plus 17 times 17 times 57. Okay, so now these are not needed. So this gives us what finally? Minus 22 times 158 minus 57 times minus, because it's going to be minus 44. Okay, what? No, it will not be minus. Okay, let me write two lines instead of writing just one. This will be plus 44 plus 17 is plus 61. But that's not how we have our original equation. Our original equation is 158x minus 57y. So in order to bring it into that form, we write this. Okay, so that is equal to 1. Now our right hand side had 7. So multiplying on both sides by 7, we now next get this. 158 times minus 154, yes, and minus 57 times 427. This is equal to 7. So this gives us a particular solution. So a particular solution is x naught equal to minus 154 and y naught is minus 427. In this solution, both x and y values are negative. Hence, the general solution is x equal to x naught plus b divided by d times t. So x naught is minus 154. Because b is 1, we just need to put b. And b is, what is b? That is important. B is not 57, b is minus 57. So minus 57t. And y is equal to y naught minus a divided by d times t. Y naught is minus 427 minus a is what? 158 times t, where t is an integer. I repeat one thing again. I am writing these formulas just for the sake of recalling them. Okay. If you have not written the general Diophantine equation and its general solution, do not use this, because if you haven't written anything else, then it becomes a question what this a and b and d are. If you make them a part of your solution, you need to write the theory, and at least you write the theorem, what theorem you are using you write its statement briefly, then you can use it. Otherwise, you just have to write x equal to this as a rough work. Beside the solution, you can of course write these things, but don't make them a part of your actual solution if you have not written the general solution or the general theory. Now, for positive solutions, we require or we seek these minus 154 minus 57t to be positive, and also minus 427 minus 158t to be positive. So here both the inequalities are same. Same means are similar. They give only one direction of the line, numbered line. By that I mean this. The first one reduces to this: t is less than minus 154 divided by 57, and the second one also reduces to a similar one, minus 427 divided by 158. If we go to the decimal values, then the first one, that is minus 154 over 57, that becomes approximately minus 2.70175, something like that, and the second one becomes t less than minus 2.70253. So this just points to what? It points to t being less than or equal to minus 3, and here there are infinitely many possibilities for t. All integers less than or equal to minus 3 will give us positive solutions. So there are infinitely many positive solutions to the given Diophantine equation one for each integer t less than or equal to minus 3, and there is of course no point trying to find out each one because there are infinitely many. So that's where the solution ends. So in this exercise we see the full spectrum of all the possibilities. In the first two we have seen that in the first one I think there was only one solution corresponding to the value t equal to minus 19. In the second one we had three positive solutions. One positive, keep in mind that whenever solutions exist for a Diophantine equation, there are actually infinitely many. That's the theory. but now we are seeking positive solutions, right? So in the first one there is only one positive solution, in the second one there are three, in the third one there is no positive solution, and in this fourth one there are infinitely many positive solutions. So that shows us the full spectrum. So that's just it. Let me just end it here itself tonight. The next upload is this coming Friday, of course, and on Friday we are going to again see graph theory. So that will be all. I wrap things up. So see you on Friday with graph theory. We are towards the end of the first preliminary chapter, after which we will start solving the exercises. There are many. Okay, so we will see how far we can go. So that's just it. So signing off, this is me, Lucifer from A Mathematical Room. Have a nice night.